We have 1 more minute. It's frowned upon to start early, so we'll just wait it out. Unless there's any questions. A question from the class can allow an early start, potentially. Any questions at the moment? Yeah.
For the sections that are going to be emphasized on the exam, those some of those questions will be represented on our practice exams. Would those questions be asked in a similar way?
Yes, absolutely. Yeah. So I would say if you look at 2017, the one we're going over, 2016, as well as sample final problems, which is a huge set of problems, all those questions have a very similar theme on the way they're asked. So there's not a big change there. And I would say, again, that's probably not the best way to think about it, but I would say that this is, in some sense, the better document because it tells you what all could happen on a final exam. These were the actual final exams given, and because it's a 2-hour exam, I can't ask everything. So while these are very powerful for getting a feel for what the actual final exam would look like, to find the scope of what kinds of questions, how they could be asked, what all is on the table, this is probably the better exam. But it looks like we're ready to start. Other questions at the moment? Did I clarify that question you were asking? Okay, you bet. Other things that to keep in mind is we were discussing last class that section 10.1, that's a great section, but it really didn't have any calculus. So I believe we agreed we won't ask a question from 10.1 because it would really just be a plotting question and nothing else. Instead, we'll probably ask 2 questions from 10.2 and possibly 1 question, maybe 2 from the other 2 sections there. And that's what we mean by emphasis. There may be about 5 questions possibly from chapter 10, but probably it's going to come around and be about the similar to what you see in 2016 and 2017 for those final exams as well. But other questions so far? Okay, also I wanted to make a comment that last class we nearly made it through this integral, but we discussed that once you got to this step right here, you need to pick a u substitution. And there's 2 good u substitutions that may work on the table. One might be u is tangent theta, which would give us a du, which is secant squared theta d theta. Turns out this one does not work because we don't have secant squared theta in the problem. So we use this as a substitution. Then the error at the very end of the class when we got to this step right here is that we're meant to undo the substitution, but we picked this. We said we had tangent cubed theta divided by 3 minus tangent theta, and that's where things went horribly wrong. So if you do write down both substitutions, my advice to you so you don't make the same mistake that I just made is cancel out the one you know does not work so you don't accidentally grab the wrong u. That's a horrible mistake to have made. Other questions with finishing out the rest of that problem? Okay, we got to writing down the triangle down here using the fact that tangent theta was x. We'll promote it to a fraction to call it x over 1, which is the opposite over the adjacent, and that's what produces secant theta, which is the hypotenuse divided by the adjacent side, and that finally gave us the right quantity down here. And that's a quantity that I would believe if I took its derivative and carefully simplified it down algebraically, we should get x cubed divided by the square root of x squared plus 1. And that'd be a great thing to check on the real final exam, except that that does take some time. So I would probably answer all the questions first, then do the checks as time permits. That means we ought to go to problem 3 next. Does that sound all right to folks? Okay, so what we're going to attempt to do is run through all the questions, but we may not be able to make it because it is a 2-hour exam and we're explaining as we go. So also keep an eye towards the final questions. Probably number 15 would not be asked, but up to 14 would be great problems. If you see we're running out of time, but you want to see the solutions to say problem 13, let's just make sure that you circle those and we get to them. Well, off to problem number 3. Any questions at all first? Okay, oh, before I get too far, anyone need a copy of the exam itself? There you go. Yep. Anyone else? Yep, you bet. I'll just leave these here in case someone comes in late. Okay, so in problem number 3, we have to find an antiderivative. What would you say the method ought to be for this problem? It's been a really long time. It's called a partial. Correct, yes. Really, the real problem on number 3 is getting through the decomposition. So this is what I would start with. Let's ignore the integral for a moment. We're dealing with x squared minus x plus 2 divided by 1 minus x times x squared plus 1. The decomposition has to deal with the denominators. So we have to first make a check, are the denominators fully factored? This was degree 1, so we're all set. Degree 2 is alarming, but x squared plus 1 is considered prime if we're factoring using just real numbers. This would be, say, x minus I times x plus I. So we leave that one alone. And say we have a divided by 1 minus x plus the second one, the irreducible, is x squared plus 1. That makes the numerator look a little bit different. It will have a higher degree of bx plus c. So that's the format of the composition. The very next step would be to clear all denominators. Does that look all right to this step? Okay, so we think of clearing denominators by multiplying this entire thing that way. That causes a distributive law in the same time, and we would get from that partial cross product x squared minus x plus 2 is now equal to 8 times, there's a cancellation of 1 minus x here, so we copy x squared plus 1. Plus, then carry the entire quantity with parentheses, bx plus c. When this whole thing is multiplied over here, the x squared plus 1 cancels, so we take a 1 minus x. Then that's the equation that we'd like to solve for a, b, and c simultaneously. And there's different methods for doing this. One method is choose specific values for x to try to make one factor go to 0. So if we let x be 1, all of this is gone, and we'll have an equation for which we can solve a for. But then there's nothing you can pick here to make this go to 0, so a different method is still possibly useful. So first, let's just get the freebie. If we set x equal to positive 1 in the above equation, then we would have 1 squared, so just 1 minus 1 plus 2 equals, here we'll have a, 1 squared plus 1 is just going to be a times 2, and throwing a 1 here gives us a 0, so the equation is now just in terms of variable a. So this is effectively 2 equals 2a, divide by 2, and a must be 1. So that reduces the equation down a little bit. Now we need to solve for b and c. And there's various ways you can do this. We could say pick x equals 0 as the next easiest value, and maybe x equals negative 1 as the next easiest value after that. Then we'll get 2 equations for which we can solve. Or we can just equate the coefficients immediately right here. Maybe let's go that route, because some problems that would be the thing to do. There may be no freebies like this one. So I'm going to mix both methods at the same time. And this is now equating coefficients, where we'll say x squared minus x plus 2 is effectively a 1, because a is now 1 everywhere you see a on the chalkboard, here included. So it's equal to 1 times x squared plus 1, so it's just an x squared plus 1 there, plus, I'll drop the parentheses next. Here we're just going to multiply all this out. So it'll be bx times 1, bx times negative x is negative b x squared. Then distribute c through that same group, and we'll get c times 1. So plus c times negative x is minus cx. And that's our brand new equation. By equating coefficients, what we're meant to do now is group x squared terms, x terms, and the constant terms all together. I might as well drop parentheses right now because that's kind of distracting. So at this stage, x squared minus x plus 2 would be equal to, for the x squared term, we'll grab x squared here. A coefficient of 1 can come from here, minus a coefficient of b. So if we distribute x squared back in, we'll get the x squared and the negative bx squared. Then we just do this again for x. So we have plus bx going here and minus cx going here. So we can say the result would be this. Factor x out, and the coefficients were b minus c. Then the last one will be for the constant term. We have a constant term of positive 1 over here and positive c over here, so we'll write just plus c plus 1. So that's our equation as it stands. So now what we've said with this last equation is that a degree 2 polynomial on the left is equal to another degree 2 polynomial on the right, but the only way that that could possibly happen is if coefficients are equal. So we set 1 equal to 1 minus b. We'll set negative 1 equal to b minus c. And we'll set positive 2 equal to c plus 1. So we already have a value for a, and that means these equations are now really easy to solve. We have 3 equations in just 2 variables. From this equation right here, we can say that b has to now be 0. Since if we subtract 1, negative b is 0, and forcing b itself to be 0. If b is 0, this equation turns into 0 minus c equals negative 1. So negative c equals negative 1. That implies that c is positive 1. Then we just double check on this equation. If c is positive 1, that would be a true statement. So it is consistent, but there is nothing to really do with that final equation. So now we have an a, a b, and a c, and we're ready to finish off the problem. Any questions to this stage? Okay, I would say that up to this point, that's possibly around 60% of the entire credit, because that really is most of the problem. To know, we have to do the decomposition. The very next step would be, we want to find the antiderivative of this thing, but now we know that this thing can be written in this way, where a is 1, b is 0, and c was 1. So we're finding the antiderivative of 1 divided by, this is some awful chalk, 1 divided by 1 minus x plus b was 0, and that's wonderful because it makes the antiderivative nicer. The next one is 1 divided by x squared plus 1 with the dx. So once we solve that, the problem is complete. So first one, the antiderivative here, because it's degree 1, would be a natural logarithm of the absolute value of 1 minus x. But this is a nasty one, because if we do a check with the chain rule, we would say the derivative of this natural logarithm will put 1 minus x into the denominator, but then we multiply by the derivative of 1 minus x, which is a negative 1. However, this is positive 1, so we fix our derivative by just throwing in an extra negative sign to account for the chain rule with a negative x. Does that make sense on that step? Okay, if it had been, say, a 1 plus x, then there would have been no correction, because the derivative of 1 plus x is 1, so no adjustments with the chain rule. Now we find the antiderivative of this one. Anyone recall what that antiderivative would be? That was an arctangent, right. So this is plus arctangent, or tangent inverse if you prefer, of x. Then the constant of integration finishes off that problem, finally. Any questions with number 3 then? Okay, so for this kind of problem, when you see this on the exam, suppose you just got stuck on the decomposition and ran out of time. What you could say to get partial credit is explain how you know the answer will be the antiderivative of this, where you leave a, b, and c as is, and then you would find the antiderivative. You would know that the first one's a logarithm, the second one's a tangent inverse, but the form depends on a, b, and c. So if you explain that, then that could be considered partial credit on these kinds of questions. So whenever you get stuck, just explain how the process should go, and I can give partial credit to that explanation. Well, let's go off to problem number 4 next. Problem number 4 says, explain briefly why the integral given below is an improper integral. It's kind of a weird question, but there will be some brief explain type questions like this one. It says briefly to indicate you really don't have to say much. You just have to say the right thing. So anyone see what makes this integral improper? Exactly. If you try to evaluate x at 3, we'd be dividing by 0. So that's the whole problem with this one. So we can say for problem number 4, f of x, which is defined to be 1 over the square root of 3x minus 9, is discontinuous at x equals 3. But since x equals 3 is part of the lower limit of integration, we cannot use the fundamental theorem of calculus on this integral. The fundamental theorem of calculus requires continuity on that closed interval. But that's okay. We can still possibly evaluate it by doing the method for the improper integral type 2. But any questions with part A? Okay, so for when it says explain briefly, this would be the kind of answer you would give. Usually these are very, very short questions. And I gave you no space to indicate there's really nothing to compute. But then we go to part B where there's tons of space. Because in part B, even though it's improper, we can still attempt to evaluate the definite integral from 3 to 6 of, I would write this as a 3x minus 9 to the power of negative 1/2 dx, just because it's easier for me to see that as an antiderivative. But the major feature of this kind of problem is the correct limit notation. So I'll use that using this chalk to say what's expected for that notation. So we have to write this out as, going to use this chalk, it has to be expressed as a limit. T would be approaching the discontinuity, but we have to specify the particular direction it approaches the discontinuity. Anyone see which way it approaches, from the right or the left? It turns out it's the right, yeah. The mental image I usually have in the back of my head for this particular process is something that looks like this. We have a problem at 3, we're okay at 6, and the variable t is going to be inserted in this way. I'll come back here and correct that 3. But what we're trying to say is we're allowing t to get closer and closer to 3, but it's always going to be to the right of 3. The reason for that is we'll be continuous on this interval. The fundamental theorem of calculus will apply, and we can use it. Then we'll analyze what happens in the limit as t approaches 3, but it's always greater than 3, which means it approaches from the right. So that'd be the second thing, or really 3 things altogether, that would have to be at the very setup of this problem. There has to be a limit, there has to be a specific direction, and the limits of integration would change. Then we just throw in 3x minus 9 to the power negative 1/2 dx and run through the process. Any questions so far with the setup? Okay, so for this problem, I think I gave about 3 points just for the setup. Then 2 points are just for evaluating the antiderivative itself and stating whether it was convergent or divergent. So the next thing we can write is that it's still the limit. I'm giving some extra space just as we take the antiderivative. I'll put the coefficients all to the left. T approaches 3 from the right. Antiderivative here, first we just increase the exponent by adding 1. So that will give us a 3x minus 9 to power positive 1/2. Very next, we multiply by the reciprocal of that exponent. That would give us a 2 that goes out here. But then we also have a chain rule situation, much like with the natural log of 1 minus x. So if it's a 3x, how would we fix that in this case? Exactly. So we can just simply divide, and that takes care of that 3 right here. So if there's a 3x, there must be a 1/3 going this way. So now we have an effective 2/3 in front of the limit. Then that whole 3x minus 9 to power 1/2, or the square root of it if you prefer, will be evaluated as we go from t to 6. That's a poorly drawn 6. So from here on out, it's mainly just copying. We'll write that this is 2/3 times the limit as t approaches 3 from the right. The next portion would be the evaluation. I'll write this as a root of 3. We're inserting t, or excuse me, 6 first, the upper limit of integration, minus 9, then minus the square root of 3 times x takes on the value of t minus 9. So that's what it would look like after the evaluations. Does that look okay to folks to that step? Okay, so then we have limit laws that are taking effect. The limit of a constant is just a constant. So this does nothing whatsoever. We just leave it in. But in this particular portion right here, t is getting closer and closer to 3. And as that happens, the thing inside the root is going to get closer and closer to 0. And the square root of 0 is 0. So in the limit, that approaches 0. And that was one point to give the appropriate limit at that step. Does that make sense to that for that particular problem? Okay, you could also think of this in terms of continuity. The square root is going to be continuous from the left, right at 3. So you can use a direct substitution by that continuity. But then that would be the root of 9 minus 9, still 0. So the whole thing turns into, we're dropping the limit because we're evaluating it, and it comes out to 0. So all we have is 2/3 times the root of 18 minus 9, which is just a 9. So the root of 9 is 3, giving us a 2/3 multiplying 3. And so the answer to this one is 2. Right, questions with that one? Okay, so that's how to get through that kind of problem. Really the major feature of that problem was the part A, knowing that it's improper and why. And part B is setting up how you can evaluate that improper integral. And also, one thing that's really, really important with these problems is making sure you put everything on there. Looks like I am missing one thing. Anyone see what's missing per the instructions? Right, I never said that at any point. That is part of the exam, to know that if you've got a 2 rather than something like infinity or a does not exist, that the original integral converges. So don't forget to do do this portion like I just did. This converges. Then that ends the problem finally. So let's go off to problem number 5. Unless there's any questions on that one. Okay, problem number 5, we have a curve, and it says, approximate the length of this curve using trapezoid rule, and immediately following in part B, we're going to use a surface area after we rotate about the y-axis using Simpson's rule. That's about how the exam will go for these kind of problems. Sometimes these are some of the nastiest integrals we've seen the entire semester. So to just make the process a little bit faster for exam, it's likely going to be Simpson rule, trapezoid rules for those kinds of problems. You'll also have the graph as well to aid in setting up the right integrals. But when you do these kinds of rules, they can be very tricky because we still have to go through the usual motions of setting up the integral. And that's where the major work would be for these kinds of problems. So for first part A, it says approximate the length of the curve. So we must know that the length of the curve is going to be the definite integral as we go from 1 to 9. That would be the domain of x specified. And this process will be the square root of something dx. Then if we were in section 10.2, it would be dx dt squared plus dy dt squared. If we were in 10.4, it'd be r squared plus dr d theta squared. But all the way back in chapter 8, it's been a long time, this one became 1 plus dy dx squared. So one thing that's really interesting about these problems, especially on an exam setting, we're told to use a trapezoid rule on the problem, so it's very tempting to just jump right to the trapezoid rule. But that's actually something you should do later. The first thing you should write down is just the formula for the length and start evaluating it. So I'm going to take the y, which is equal to e to the x, and run through the process of first calculate dy dx, square it, add 1, and so on. That way we'll know exactly what the integrand is to use on the trapezoid rule. Oh, e to the negative x, thank you. That'd be a horrible mistake to make on the exam. But if you did make this mistake on the final exam, then I would probably just regrade the question as if it was that.
It's e to the x minus x.
Oh, e to the x minus x, I got you, sorry. Okay, so it's slightly nastier, but it's the right problem, thank you. So first things first, we'll calculate dy dx, or just write y prime if you prefer. That's really up to your preference. We hit the Leibniz notation really hard in chapter 10, mainly because there's multiple variables. Also, it's something to get used to in calculus 3 as well. So dy dx, in this case, is first derivative of e to the x. That's itself, it's nice, minus the derivative of x, which is 1. So we've got that portion down. Next thing to do right after is just square that whole thing. So I'd probably go like this, just on the same line, square it, and it would look about like that. And that would give us, oh, hang on, don't forget to square it. That will give us our dy dx squared. So let's multiply that out next. This will be first e to the x times e to the x. That's e to the x squared, or e to the 2x if you like, since the exponents would add together in this multiplication. Then here to here is negative e to the x. There's negative e to the x again. So there's negative 2 e to the x. Finally, here to here is going to be plus 1. So that's our dy dx squared. Then we don't have to go too far with this stuff because we're not trying to do it exactly. If we were trying to do it exactly like we did in the homework and in class, then this could be a very long process in and of itself. Instead, I'd probably take over, come back here to the length, and say that this is now the definite integral from 1 to 9 of the square root of. There's a 1 here, so I'm going to combine it with this to get the 2. To get e to the 2x minus 2e to the x plus 2 dx. Then we've set up the length for the integral. The next process is we're going to approximate it next, but let's record this very, very key fact that will expedite writing down all the details in the final exam. The integrand is f of x equals the square root of e to the 2x minus 2 e to the x plus 2. So just writing this down indicates to me what the integrand is, so that I know that you know what's going to be approximated exactly. So next, we're using the trapezoid rule. So this is approximately equal to t, was it 4? I forgot. Oh dear. I'll just grab another one. This one was trapezoid rule with n is 4. So let's say it's approximately equal to t4 itself. But that's going to be equal to a delta x divided by 2 multiplying f at x naught. And the pattern for this one is very similar to Simpson's rule, except the middle terms are just going to have coefficients of 2 all the way down the line, coefficients of 1 on the very ends. So instead of going 4, 2, 4, 2, ending with a 4, we'll just go 2 f at x1, 2 f at x2, 2 f at x3. We're ending at f at x4. So this would be just the formula for trapezoid rule with 4 subintervals. Does that look all right to folks to that step? Okay, so we're just about done. This is probably what I would do very next on this exam to finish this out. I'd write down below, somewhere in the scratch region, delta x is the upper limit of 9 minus the lower limit of 1 divided by the number of subintervals in the problem, which is 4. So this is 8/4 for a 2 altogether. So we have our delta x, and I'd probably write down somewhere that x naught is the lower limit of integration, which is a 1. That actually gets us all the information we need to finish out the equality that we have left hanging. So we can say delta x is 2 divided by 2 is just a 1 here. So I'll just write a 1. Just to emphasize, we did it, that's been evaluated, nothing was forgotten. Multiplying the bracket, which contains the group, first it's f at x naught, but x naught is always the lower limit of integration, which was 1. Then it's plus 2 f at, and what was the trick to get to the very next input to the function? It would see what the next evaluation should be.
3.
Yeah, it would be 3 altogether. Thanks. So we would have 2 f at 3 plus 2 f at 5, and all we're ever doing is adding a delta x to get to every last value. So as soon as we knew the starting point was 1, delta x was 2, just add 2 all the way down the line. And there is a check here because we had better end at f at 9. So let's check this out. It'll be plus 2 f at 7. So that goes this term goes to this term goes to this term goes to this term. So yes, we're at f at x4, no coefficient other than a 1. And if we add 2 to 7, this would be f at 9. And close the bracket. So this would be a decent stopping point. You can write out a whole lot more, but notice you've said everything, what delta x is, what x naught all the way through x sub 4 is, and you've also said what the function f itself is right here. So if these are the elements that you have on your paper, I would say that that's a full solution. You know how to set up the integral, you know what the length looks like, and you know what the trapezoid rule is if you write down that much detail. And if you really want to, you can always evaluate this later. Any questions about that problem? Okay, and by the way, by evaluating this later, we won't have class meetings after the final exam, but your folks are welcome, if you'd like your final exam back, to just email anytime. Then at some point, it could take a minute, but at some point I'll scan your exam and email it right back to you. Other questions so far? Okay, let's go to the part B then. In part B, we're now doing a rotation of this curve about the y-axis. So this is probably what I would draw on this actual exam. The sketch starts at 1, it ends at 9, and it looks like it's, well, it's meant to start at 1. It's very low, and then it grows extremely rapidly, about like this. We're taking this entire curve and rotating it about the y-axis. So the rotation is going this way. That means there'll be a point anywhere along here. Let's suppose we picked this value x. X has to range from 1 to 9, just like it's doing over here in the integral. But as soon as you pick an x, there will be one point on this curve. That entire point has to rotate about the y-axis. So there's a mirror image of that point way over here. The thing that we really need in order to get the format correct is this radius. If we do this rotation about the y-axis, the radius is always just x itself. And then that sets up the right formula for the surface area. If we rotate about the x-axis, the radius instead would have been a y, but then y itself is e to the x minus x. So it's a nastier looking integral. But if you're just using Simpson's rule in part B, it's not too bad to get through. But any questions with this diagram so far? Meant to be this with just a little bit extra written in. Okay, so this is how part B would run then for the next portion. We'll say that S for the surface area is now the definite integral from 1 to 9 of 2 pi times, we always throw the radius right here. But in this diagram, the radius was x. Whereas if we rotate about the other axis, the x-axis, this would have been a y, which we would have had to unsubstitute. Then it's going to be multiplied by the square root of 1 plus dy dx squared dx. So that'd be the setup of that definite integral. And things to keep in mind is that when you take these final exams, they can be kind of stressful, but also it's always good to kind of go slow, take some deep breaths, and sometimes there's massive shortcuts because we've already done the root of 1 plus dy dx squared, so we don't have to redo that. But actually, 2 years ago when I gave this exam, about 20% of the class did in fact redo that. So don't make that mistake. You do have a freebie from part A. We can just say that the surface is immediately the definite integral from 1 to 9 of 2 pi x square root of, it went e to the 2x plus, or excuse me, minus 2e to the x, and then plus 2 with a dx. So the surface area would look just like that. Oh, another comment to make is we've also done some interesting problems in these contexts where the curve could have been given in, say, this way. X is equal to maybe y cubed plus 4y, just something random like that. But we're going to kind of stick to the normal functions where x is independent and y is dependent. So it'll be similar to what we see here. But the rotation could be either the y-axis or the x-axis. Any questions so far then? Okay, at this stage we're just nearly done. We're going to repeat what we've done before, but keep in mind, this is an amazing device for just writing out the result quickly, and I could tell by substitution what you expressed over here. But over here, you cannot reuse that function. The new function is f of x is 2 pi x square root e to the 2x minus 2 e to the x plus 2. There'd be no dx because this is just one big symbol with the the definite integral sign. So make sure you indicate the new function for the new situation. Then beyond that, we can say this surface area, S, is approximately equal to, we're doing Simpson's rule with n is equal to 8. That was kind of nasty. I don't know what I had against that class. I'll probably keep it a little bit lower. I don't know if 8 is really the best thing to do on this one. But if you're going to calculate S8, once again, you need a new delta x. And this is a new delta x because we have a different number of partitions. This time it's 8 subintervals. So we go 9 minus 1 in the numerator, once again, divide by 8. Oh, that's probably why I did that. You get 8/8, which is 1, and it just makes the arithmetic a little bit better in this problem. That's a bit of a compromise. Let's run through the rest of it and finish off the problem. Any questions first? Okay, the last details to write is our starting point is always x naught, and this time it's still a 1, so now we can say the surface area is going to be approximately equal to delta x divided by 3, this is the S8, multiplying, maybe let's do this in a slightly different way. Delta x was a 1, so I'm just going to throw in a 1/3 immediately. Then I'm going to write f, I want to put in x naught, but we know x naught to be 1. So let's go for the result right away. Does that seem all right to folks? Okay, it's effectively this kind of formula. However, if it's Simpson's rule, we'll do 4, 2, 4, ending on a 4, starting on a 4, but repeating 4, 2, 4, 2 as many times as necessary. So the next one will be plus 4, f at, delta x was a 1, so we do at 2. So plus delta x. Then we're changing this to a 2, f at delta x, so it's f at 3, and then so on down the line. So really this is just a lot of copying. But I guess the reason for 8 subintervals was just to make the computations a little bit nicer down the line. So that probably saves time in the end. So this is plus 4, f at 4, plus 2, f at 5, plus 4, f at 6, new line, plus 2, f at 7, plus 4, f at 8, and keep an eye on the target always. We're only going up to f at 9. And when we go to the endpoint, we drop the coefficient. So this will be f at 9. So with all this information here, since you've indicated f of x on the exam, it's all there by substitution. And I would consider that full credit. Any questions with that one? Okay, so that was lengths and surface areas. That takes us to differential equations. We can't ask all the differential equations. So I think another great way to study for this exam, those documents are obviously really great, but your exam 1, exam 2, and exam 3 are also really, really great materials for the exam. And if one of them went missing, I do have the blank exams that I could always send you. So you're welcome to send emails asking for them. I think some of them are actually on the Moodle website as well. Let's solve this differential equation on number 6. This one is a first order linear differential equation which has a specific method for solving. First, let's write down the method briefly to explain why we're doing what we're about to do to this equation. The method says if you have y prime minus a function p of, let's let the variable be t, because it's t in this problem, times y, and if it's set equal to a q of t, then the method is to multiply both sides by I of t. This was the so-called integrating factor. It's a pretty mysterious looking formula where it's a basic exponential to the power of whatever you have up here. So the substitution would look about like this. But also keep in mind, we didn't always have to do that. So these particular problems, if you look before you leap, you can undo the product rule immediately without actually using the integrating factor. But in problem number 6, the coefficient of y prime is 1, much like in this formula. So that indicates there really isn't any great shortcut this time, unless the coefficient is just right. So we're just going to go right through the method. So no shortcuts on this one, sadly. And the method is going to look about like this. First, let me copy the equation. Y prime minus 3y is equal to t e to the 3t. So we just pause that equation for the moment because we have to solve the integrating factor problem first. So let's go to yet a different column. Probably a 2-column system is a good idea on this particular problem. We want the p of t function, which is, I of t function for integrating factor, which is the antiderivative of something. Anyone see what would go in the antiderivative position here?
Just 3y, right?
Almost, really close.
Negative 3y?
It would just be the -3, yeah.
Oh.
So in order to, oh, hang on, sorry, there is a problem right here. That should have been a plus, sorry about that. So it should be y prime plus a p of t. So if we see a negative sign, we grab all of the -3 for the correct formula. So we go, integrating factor is e to the power of -3 dt to match this -3 there. Also because the correct formula should have a plus, so we take this sign as well. Does that make sense so far? Okay, so we have the all-time best antiderivative right here, but the problem still has to be solved. So we have e to the power of antiderivative of -3 with respect to t is just a -3t. And that's the quantity that we need to multiply all 3 sides by. So that gets us started. So we take this and multiply it here, here, and here. So I would write e to the -3t is now multiplying, oh, the chalk is over here, y prime, then -3 e to the -3t times y would go here, and that would be equal to t e to the +3t times e to the -3t. So that's our second step. Get the integrating factor first, and then multiply all three portions or terms of that differential equation by it. And what we can now say is, if we look at this really carefully, the derivative of e -3t is -3 e to the -3t. We also have y prime here and copied y here. So we can, in the very next step, write out something like this. Dx of e to the -3t y is now equal to t e to the, or just t. There's a cancellation going that way. So that would be the very next step. Any questions with that step right there? It looks weird to write this, but if you were to take the derivative of all of this using the product rule, you in fact get exactly what is up here. So the next step after this, anyone recall what it would be? Yeah. Close, but that would be if it was a separable equation. You're on the right track for that one. If it was, say, something like this, we would do exactly that. So it's really this term right here, the -3y, that changed the method a bunch on us. Anyone see what the next step should be then? Turns out the trick is, once you get to this stage, you've multiplied all sides by the integrating factor, you've undone the product rule. Very next thing to do is take the antiderivative with respect to t. So it would look like this very next. Or to just say that that was the very next step written in the same line. But now we have a nice formula right here. It says take the antiderivative of a derivative. That's a full-on cancellation. The dt is also the integrating sign, so cancel the dt if you like. And now we get e to the negative 3t times y is the antiderivative of t, but that would be t squared divided by 2. And there really is two constants of integration because we integrate the left and the right side, but we usually, in this context, consolidate it to just one side, the right-hand side with the independent variable t. So we take the antiderivative of both sides, and notice this actually is the solution in implicit form. So we have two things to do. We want to solve the initial value problem, so we're going to solve for c. Final thing to do is to get the explicit solution by solving for y. Any questions so far to this step? Okay, so you can either solve for y right now and then solve for c later, or solve for c right now and solve y later. Really, it's completely up to you. Let's go for the c right now. The initial condition was that y at 0 is equal to 1. We write function notation here because y is in fact a function of the variable x. And all this just means is that when x equals 0, y must be equal to 1. So we'll plug in that information right on this line. Oh, I said x again. I'm not used to variable t. But it should be when t is equal to 0, that independent variable. We would have y as 1. So I'm going to throw in a 0 on the t here. That would give us a e to the 0. We're putting in a 1 for y, so now it's e to the 0 times 1 is equal to 0 for t would give us just a 0 outright here, plus c. So that's a really nice equation because the right-hand side is just c, and the left-hand side is just 1 altogether. So that solves for this c right here. So now we have e to the negative 3t times y is t squared divided by 2 plus 1. And the whole problem is finished. We have y in explicit form as soon as we divide. And if it's not possible to get the explicit solution for y, the exam would say so. But in fact, in this context, for the first order linear differential equation, it's a long word, you can always solve for y explicitly. I mean, you might have to use a fundamental theorem of calculus, but I probably would not do that to you. So the solution is finally y equals t squared divided by 2 plus 1 divided by e to the power of negative 3t. And there's many different formats you could write this in, but if you stopped right there, that'd be all right with me. You don't have to simplify any further. Any questions with that one? Okay, so there's not a lot of differential equations that would be on the exam, mainly because we didn't spend a whole lot of time on differential equations. So expect something kind of like this, or possibly a separable equation. Those were the major ones that we looked at. Let's go off to next problem number 7. Problem number 7 is purely a true or false question. So no explanation is required, just means you could write the explanation if you like, just to convince yourself it's really true or really false. But I'm just going to look at purely the true or false. For us, let's write down the explanation just so that, well, I mean, this is meant to be a review, and we'll be prepared for the next set of problems that look like this. Probably not a lot of questions like these. I might just add a single one, much like on this exam. Let's go from the start to finish. Problem 7 says the sequence 1 over n, as n goes from 1 to infinity, diverges. Would this one be true or false? Some say false. Any for true? Some for true. It's actually really kind of nasty in some sense. The one thing that determines whether it's true or false is a separate question. Would this be a sequence or a series? It's a sequence, right? If it's a series, we'd be using the summation symbol because we'd be adding every single term, of which there's infinitely many, all together.
So because this is a sequence, that means we determine convergence divergence by a limit, and that's it. We take the limit as n goes to infinity of 1 over n, which is 0, and that implies convergence. So this would be, I think this is part A, false. But if we're looking at, say, this series with a summation symbol, that would be the divergent harmonic series. And you could show that that, in fact, does diverge using, say, the integral test. And the book gave an alternate proof of that fact. But written in this way, you're just dealing with a sequence. And every time you're trying to determine convergence versus divergence for sequences, it's always just going to be a limit. So those are kind of the nicer problems. So let's go off to part B next. Part B says, if the series A sub n converges, then the sequence must converge. Turns out that this one is true. Anyone see why this one ought to be true? It's a little bit different, right? Because we're told the series converges. We're meant to conclude the sequence must converge. This turns out to be true, and this is a way you can justify why it should be true. We'd like to take, because we're dealing with a sequence, the limit as n goes to infinity of A sub n. Anyone know what that limit ought to come out as? There's a bit of a trick to seeing it. We were saying that this converges, but this convergence means as you go from 1 to infinity of summation A sub n, then A1 plus A2 plus A3, but now there's infinitely many terms, so plus all the way to AN plus AN plus 1 plus forever turns into some number. I don't know what it is, but let's just say it came out as 7, just for the sake of a concrete explanation. So if this equals exactly 7, would you folks agree that if we're adding infinitely many things together that came out to something finite like 7, the terms should probably be getting smaller and smaller and smaller as we go along? Would you all agree with that? Yeah, for example, everything was, if the sequence was converging to, say, 1, then we'd be adding things that are close to 1 infinitely many times, often together. That would be divergence for this right here in the series. But because the series converges, that implies A sub n is getting smaller and smaller. And there's no limit to how small it gets in absolute value. So in fact, it would be 0 in the limit itself. And that gives us convergence to the sequence as well. Not only does it converge, it converges to 0 specifically every time the series would converge. Any questions about that so far? Okay, I think those are the trickiest ones. Part C is maybe not so bad. Well, it's really a definition from a long time ago, so it could be kind of weird. But we're told that the partial sums of the series, as n goes from 1 to infinity, of A sub n is of this form. Sn is equal to n plus 4 divided by 2n minus 1. Then the problem goes on to say the limit as n goes to infinity is 1/2. Yeah, that checks out. It's a rational function, horizontal asymptote at 1/2. So since the limit of this is 1/2, this must diverge according to that. Would you folks say that's true or false? I feel like it's really close to true because it feels like the test for divergence. Would you folks agree with that? But notice that in the test for divergence, this is what the work would look like instead. You might have something that goes from 1 to infinity, summation, maybe it's n squared plus 1, divided by n squared minus, let's go with plus 4, so we don't have any discontinuities. Then if we took the limit as n goes to infinity of n squared plus 1 divided by n squared plus 4, this would be 1 in the limit, which is non-zero. So we could say that this diverges by the test for divergence. But what's different in this problem is we were told that this is not A sub n. This is the sequence of partial sums. And we're told the sequence of partial sums, not the an sequence over here, is what converged to 1/2. This means that the summation as n goes from 1 to infinity of A sub n is equal to the limit as n goes to infinity of S sub n. And this occurs whenever, or provided, the series converges. Whenever the series converges, it's always equal to the limit of the sequence of its partial sums. This limit did converge to 1/2. So that means this, in fact, converges itself. It converges to 1/2. You could literally write it equals 1/2, and you're all set. But the problem says the series diverges, so we have to say false on this one. Again, this was a horrible trick question. I think I curved the exam a little bit 2 years ago, specifically because of this kind of question. It was nasty. So watch out for that. The sequence of partial sums gives you a totally different outlook on this kind of thing. And that's going through the original definition in section 11.2. I think that's a really good section to revisit, 11.1 to 11.2, because as you're seeing with these parts A, B, and C, they're all about what is the difference between a sequence and a series. And that gets really fuzzy once we are at the very end of the class. So check out those sections, 11.1, in particular 11.2, and it helps a lot with these. But let me give a final assessment to this part. It's false. And let's go on to the next. Any questions at all with part C? Okay, I should mention, because I lost track of time, we are going to end in about 12 or 13 minutes. Are there questions folks would like to definitely solve before we call it a day?
Can we do number 10?
Yeah, you bet. And we're definitely not going to get to all of them, but I believe we have solutions here. Not a lot of people came to office hours. Some people did. But if you are dying to find solutions to some problems, you folks are welcome to take, say, cell phone pictures, things like that, at the end of class. And then once I am near a scanner, I'll be sure to upload these as soon as possible, probably sometime on Friday, so that you can also take a look at those. But this was problem number 10, was that correct? Gotcha. So problem number 10 says, use the established Maclaurin series formulas to find the Maclaurin series of each expression. So this exam was written in a particularly different way in 2017. On the very front cover of the exam, I just gave people Maclaurin series formulas. And there's a whole bunch in section 11.10, lovingly called table 10.1, I think. But for this kind of question on the new exam for 2019, I would just give the formula in the context of the problem. So that saves the need for writing things at the front cover of the exam. I think a lot of people just didn't realize it was even there in 2017. So the problem would start by providing this formula. Sine x is the summation from 0 to infinity, -1 to the n, x to the power of 2n plus 1, divided by 2n plus 1 factorial. And this has a radius of convergence, which is infinite. So in part A, it says find the Maclaurin series for sine x divided by x, state its radius of convergence. So let's do that next. Yeah.
So people have to write down the Maclaurin series.
Oh, you wouldn't have to, yeah. So if you needed a Maclaurin series, I would provide it. Yeah, that's a really good question. And also another question to clarify that is, there might be one problem. I'm kind of debating on it. Problem number 12 says, actually construct the Taylor series using the definition. So if the problem says to do that, that's when we do our lovingly two-column system, one's being the derivatives, the other's the derivatives evaluated at the center, and we build up this series ourselves. But for this particular problem, it's going to be provided, so you wouldn't have to fill that out on your note card, unless you just like to have it. If it's comforting to have a Maclaurin series with you, you can bring them, because you could bring anything on that sheet of notes. Other questions or comments so far? Okay, so let's get to this part A. which says find the Maclaurin series for sine of x divided by x. But really, at the heart of this question is it's just a substitution type question. I'd rewrite this as 1 over x times sine x, just to help with the substitution portion. Then this would become, after we substitute, equal to 1 over x times the summation from 0 to infinity, negative 1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. So we would write that out, and I would possibly give full credit to this, but it's still not a very good spot to leave it on, because that would cause part B to be harder. So it's always a great idea when you write down a Maclaurin series, simplify it as much as possible, especially if you know you may have to do more with it. And the way this simplifies is base x over here and base x over there can combine. So now it's a summation from 0 to infinity of negative 1 to the n. The power here decreases by 1 after the division. So now it's x to the power of 2n. And we divide still by 2n plus 1 factorial. So now we have the Maclaurin series, and the second part of the problem says state the radius of convergence for each part. What's interesting about this is we know different methods for doing this. Just hit it with a ratio test and you would get the radius of convergence. But it's totally unnecessary. Anyone see what the radius of convergence just has to be? It's the same, exactly. So if we modify a Maclaurin series by multiplying by the reciprocal of x, we haven't changed the radius of convergence. It would still be infinity. In fact, we can differentiate this, or integrate those two things, and we still would not have changed the radius of infinity. And the question is written in a way to kind of be a hint for that. If it says to just state something, whether it's this problem or another problem, you just have to state it. Work wouldn't really be required. So it's saying state the radius of convergence means just put r equals infinity, and you've got it. Now let's go off to part B. Any questions so far? Okay, so in part B, it's really just another substitution. We want the antiderivative of sine x divided by x with respect to x. So we'll already have the Maclaurin series representation of that particular function. So we can say now this is going to be the antiderivative as we sum from 0 to infinity of, I'm just copying at this point, that last answer, negative 1, x to the power of 2n divided by 2n plus 1 factorial and dx. So we want to take that antiderivative. And again, what's interesting with this antiderivative is the variable we've indicated right here. So we're doing the antiderivative with respect to x. N is just an index for summation, which means negative 1 to the n. The 2n, well, that's not as critical because that's wrapped with x. But the negative 1 to the n, the 2n plus 1 factorial, are constants in the process of taking this antiderivative. So even though it looks really, really crazy here, focus on this, and you would get summation as n goes from 0 to infinity of negative 1 to the power of n, x to the power of 2n, and something changes. Do we go up or down in this problem? Correct, we go up by 1. We're not replacing n with n plus 1. We're just simply adding a 1. We would replace n with n plus 1 if we did in fact use, say, the ratio test. So if we get a new power on the antiderivative, don't forget to immediately power or divide by that new power. 2n plus 1 factorial is already there. And that's an antiderivative, but we want all antiderivatives, so it would be missing so far. Right, we need that constant of integration. It can be really easy to forget, but it would have to go in that problem. We usually call that like a half a point. So if you forgot the plus C on this exam, it's probably not going to be a very big deal. I don't think anyone has failed this class because they forgot the plus C. But also when I grade this as a final exam, I would only take off a half a point once. So you wouldn't be dinged repeatedly for the same mistake. But just remember your constant of integration
and you'll get that 0.5%, which could make all the difference, but probably not. Other questions about that problem? Okay, we still have 4 more minutes. Any last problem folks would like to go over?
I got a question.
Sure.
So for the exams on Moodle, are you going to post the solutions to them, like the final exam problems?
Ooh, I thought I had it for this one, but I think I do have it for this one right here. The sample exam problems, this is just a long list of decent questions. This one does have solutions at the end. And sorry, I thought I had it for the 2016 version. I know I didn't have it for this version. But yeah, I'll upload the 2016 solutions afterwards. I'll probably focus on this one first, and then I'll start solving and uploading the next one. Other questions so far?
That final exam,
Mhm.
consider that like a database of questions?
I would say that wouldn't be inappropriate. That'd be a good way to go. But add to your database exam 1, 2, and 3, and it's more complete. Yeah, that's a good point. So usually when I write the final exam, I do a couple of things. I solve it myself and make sure none of the problems are annoying, like awful arithmetic, just too long, things like that. Then the second thing I do is I look carefully at those questions and I decide, is the question appropriate? Have we asked it on exam 1, 2, or 3? Or is it on one of these sample exam packets? Or is it on the sample final exam problem, that long list? If it is on one of those lists, I would say, yeah, that's a decent problem. If it's not, then I look at it even more carefully and ask myself the questions, did we do it on homework? Did we ever do it on the board for lecture? If it's no to all of those, possibly I would just change the question. If it's a yes to all those, I might run it on the actual exam, but I would think of that as kind of a special problem where when I start grading, I'll see how people do, and I may curve by the entire point value of that type of question. It'd be like a challenge question in a sense. Does that make sense? Okay, if I did that, I might just, down the line, if I felt like the challenge question was too inappropriate of a challenge and could possibly lower your grade if you spent too much time on it, I'd probably just say this one is for extra credit outright. So that way you can have it at the very end of the exam. You'll know that you don't want to waste time on it, only consider it when the exam is complete. So there may be a bonus question just like that. Other questions about the exam itself? Still have a good, 50 seconds? Okay, we'll end a little bit early today, which means office hours has started. So what are your questions so far? I'm just joking. Your folks are welcome to leave if you need to leave. It is already quite late. But if you do have questions, feel free to stick